guys, we're going to explore some power functions, a few characteristics of them. The first one that we're going to graph is referred to as a quadratic. I can tell specifically by the equation because it's squared. It's squared and it has a power of 2. So that means when I create a table of power 2, right? Let's keep our numbers relatively small here because we have to graph this, and if I square, for instance, 10, I get 100, and I don't have 100 y values on here. So we have x, and we have y, or as we refer to as f of x. So I'm also going to go on the right-hand side of 0 and graph some of the positive values. Okay? So negative 4 squared, negative 4 times negative 4 is 16. I obviously can't graph that order pair, but negative 3 times negative 3 is 9, and I can graph that order pair at negative 3 and go up 9. Now negative 2 squared is 4, it's positive, note, I can graph that. Negative 1 squared is 1, and it's positive, that y value is positive. And then 0 squared is, of course, just 0. So we can square that, right? So I have 1, 4, 9, 16. So 1, right 2 up 4, right 3 up 9. And as I can see, this curve that we create here is symmetric. It folds on top of the other. So quadratic functions are even functions, typically in this form. And some key characteristics here, another thing to notice, is that as my x values decrease, I can look at the table, my y values, my f of x's, they're increasing. So we might write as x goes to negative infinity, my y values, algebraically, we might write f of x goes to positive infinity. Graphically, we could just put a little positive infinity signs in order to express that the end behavior here is infinity going towards the left. Now, how do I express that going towards the right? Going towards the right, as x goes to infinity, my y values or my f of x values go towards infinity as well. They increase. They point upwards at the sky. Well, what about when we get to a cubic function? So this is a cubic function. This is a cubic. I'm going to create my little tables here. So I have x, I have y. I'm going to go cubic. So I'm going to keep them relatively small because, wow, they get big really quick. So if I go with 3 squared, negative 3 squared, I get negative 27. If I go with negative 2 squared, negative 2 times negative 2 times negative 2 is negative 8. These are all negative, and then the x is negative. So very different from that quadratic, and it's something worth noting. So negative 1 cubed is negative 1. 0 cubed is 0. 1, 2, and 3. 1, 8, and 27. So we can go ahead and graph that. So negative 3 and negative 27, that order pair won't find on this graph, but negative 2 and negative 8, I go down 8, right? And I can grab that. So I'll go for -1, left 1, down 1. And then I have 0, 0. And I go right 1, up 1. And I go right 2 and up 8. And I can grab my curve. All right. So what's notable here, it is symmetric. It's oddly symmetric. But the distinction would be in what's happening with these x values and these y values. So this quadratic only produces positive y values, no matter what the sign of the x is. Over here, this produces positive and negative. And there's a y to that. There's a y. And we're going to write because the power is equal. The exponent is equal to is even. So when I have an even exponent, I know for sure all my y values are going to be positive. And the only way it'll be negative is if there's a negative in front, and you'll see that later on. So right here, this equation only produces, oh, should I put only? No, because they're positive and negative. So it produces positive, both, not only, both positive and negative y values. I'm taking the time to say that because it's relatively important. Okay, and you'll see questions about how y does that later on. So in behavior here, as my x values go towards the left, so as they go to negative infinity, as they go this way, right? These y values on the graph actually go down towards negative infinity pretty rapidly. What about when x goes towards positive infinity? The y values go up towards positive infinity. Okay. So now we're going to graph y equals x to the 4th. Okay. So keeping my numbers relatively small. So negative 3, negative 2, negative 1, 0, 1, 2, and 3. Alright? So I have 81, it's positive, 16, positive, 1, 0, 1, 16, and 81. So these are really big numbers. So that's why I kind of kept them very small. So how might I graph this? So this is 0, 0 right here. We have 1, negative 1, and we have negative 1, 1, and 1, 1. So this is going to go pretty rapidly up. Very close. So if you notice, the bigger that exponent, the closer it gets to the y-axis, the closer it squeezes into the y-axis, right? So this is a quartic. It's a quartic function. It is even. The end behavior has me saying as x goes to negative infinity, f of x, of course, goes to infinity. As x goes to positive infinity, x goes to infinity as well. Produces only positive values for this particular function. So now we're going to move on to, these were our power functions. Now we're going to move on to root functions. Root functions. As you can see, if I have a fraction, it's pretty much going to get a root here. So let's look at some tables of values here. Let me make some adjustments fairly quickly. Some adjustments there. Right. So these roots, while our power functions, these y values tend to appear to be concave up or concave down. So we're going to make a note of that at the bottom. But for now, we're going to create our table of values here. Okay. All right. So we have x, we have y, Ooh, messed it up. Looking bad there, guys. Let me create a better table of values here as well. All right, so we have we're gonna have just looking at this square root numbers, I can get the square root of between 1 and 10. I can get the square root of 4. And in fact, I will do -4 and -1 and 0 and 1 and 4. So the square root of -4 actually just literally we would write it does not exist. You can't graph something that doesn't exist. It does not exist. All right? But you can graph the square root of 0. It's just 0. The square root of 1 is just 1. The square root of 4 is just 2. Another pair that we could do would be 9 and 3. So, yeah, works out. All right. So, 9 is right over here. So 9 and then up 3. So I have a point right here, right there. And then I have some 9 right there. Sorry, I'm having a little bit of trouble writing. Then I have 4. Then I have 4 and up 2. Then I have 1 and up 1. And then I have 0 and 0. So I'm going to connect those curves here. All right. And so as we get bigger, as we look at these x values, as they get bigger, my y values do get bigger as well. So I could write a statement that says as x goes to infinity, my y values go to infinity as well. As x goes to negative infinity, or it's literally 0, my y values, where'd they go? What's the smallest y value I have? It is to the right, to the left, I mean, and it's 0. It's 0. Like I can't go past 0. Now with this square root, it's a root, and we'll take a note of that, and we'll make a distinction between these roots and these power functions up top. So let's look at our next root here. It's to the 1/3, and technically roots are powers, but we want to make the distinction that they're different than the nature of integers. So my table here, just going to do it. I have 0, 0, And of course, we have 1 and 1. Right? If I get the cube root of 2, not going to give me anything. Cube root of 3, not giving me anything. Cube root of 4, too hard to graph. Cube root of 5, that y value is too hard to graph. So same thing with 6 and 7. But the cube root of 8 is 2. It's 2. So I'm going to connect the portions of this portion of the graph. And it looks very similar to this square root graph over here. Now, if I wanted, I'm going to create a table here. If I wanted to create a table of values for this, I already have 0 and 0, 1 and 1, 8 and 2. Let's go backwards. Let's do -1. So cube root of -1 is just going to be -1. And so we actually can have negative values for and negative order pairs for a cube root function. Can't do that for the square root function. -8 and -2. All right, so I'm going to graph this other portion here. So 1 and -1 and -8 right over here and down 2 right here. -2 down 2. Graph that curve. So let's look at what's happening to these values. So as x goes to the right, my end behavior suggests it's going to positive infinity. As x goes to the left, my end behavior suggests that it's going to negative infinity. And for this fourth root, that's how we say it, a fourth root right here, something similar happens. So I'm actually going to type out these values here. Let's type out these values. And we have our x's, we have our y's equaling f of x, right? Okay. And what might those look like? So I'm going to make my text a little bit smaller. All right. So we have, let's work with, what can I get the fourth root of? Well, if I take a peek at my y values on that power function of 4 top, I might get a clue. So it looks like I don't want to go bigger than 81. Wow. That's a big number. So let's go with 81 here. So the fourth root of 81 is 3, so that's too big. Fourth root of 16 is 2, and we'll do the negatives for this too. Fourth root of 4, oh, too big, too messy with that one. Fourth root of 1 is 1. Fourth root of 0 is 0. Let's do -1. Fourth root of -1 does not exist. Fourth root of -16 does not exist. So we actually don't graph on the left-hand side of the y-axis. So it's only over here. So let's get to graphing. I'm going to create some points here. I'm going to make them big dots. So 0, 0. Let's get the pointer. Got the wrong one. So big dots here. So 0, 0. Okay. I have 1, 1. And I have 16, 2, which is really big. So it looks like this, guys. and it's increasing, but very, very, very slowly. So as x goes to negative infinity, my y values go to 0. So if I go to the left, if you look, my y values literally stop at 0. As x goes to positive infinity, my y values, they go to positive infinity. They're going up very slowly. They're creeping up. And this is the I call these functions the creeper functions, because their ability to rise or fall, if you would say, makes it hard for them to increase or decrease. So let's look at these functions really quickly. So if you look at all of the power functions where the exponent is an integer, those functions, we're going to refer to them as power functions. Those functions are typically concave up or concave down. They are shaped upwards. They're more steep in their climb, whereas our root functions are different. They curve to the left and they curve to the right. So let's write a statement about that. So power functions whose exponents are integers typically curve up or down. Up and or down. Whereas our root functions curve left and or right. And the and or comes with those odd power integers. Comes with those odd power integers. Okay? So moving on to the next page here. Let's go here. All right. So I'm going to create a separate video for these. These are distinct and different, but yeah, thanks.